Okay, today I want to talk about carbohydrates and the couple different ways that we can represent them. So I want to start off with Fischer projections, which are kind of if you take a long chain carbohydrate. So I have kind of my molecule here. And if I was to take this thing in all of its three-dimensional glory and then flatten it, then what I end up with is my Fischer projection. So I want to talk about what we're looking at and how we interpret this, and then we'll talk about how this long chain relates to the ring structure that we see and think about when we think about carbohydrates. Because when we think about monosaccharides, which are the monomers that make up carbohydrates, we usually envision them as a ring. There's value to both models, and they exist in both ways, but more often than not, we'll see these monosaccharides as ring structures when they're in their biologically functional kind of configuration or conformation. So I want to talk about how one begets the other and kind of what we get information-wise from each, because there's reasons, there's reasons that we have each of these different models. So this kind of looks like a Lewis dot structure. It's very, cardinal directions. It doesn't give you a lot of sense of the geometry of the thing. It just looks like a giant snake. Now we know that carbohydrates are kind of polyhydroxyls or polyalcohols, so they have these alcohol groups that are sitting off this main chain. When we put this Fischer projection together, then we want to put the side with either the aldehyde or the ketone at the top. So this is going to be our carbon number 1 here, and it's always going to be at the top. So this is either aldehyde or ketone. In this case, it's an aldehyde, obviously. Aldehyde or ketone. So if I'd have the carbonyl, that carbon double bonded to the oxygen, on the second carbon here, then that would be a ketone. So this makes it, because this is an aldehyde, this is an aldose. So remember, ose is the ending for carbohydrates. If it had the carbonyl off of the second carbon there, making it a ketone, it would be a ketose. Now I'm going to number down. So my 1 here is my aldehyde group, 2, 3, 4, 5, 6. So you'll note then that I have carbons in the center that are sandwiched by achiral carbons on each side. So my carbon number 1, C1 here, is not chiral because it's only attached to 3 things. So it can't be chiral because one of the things that has to be true about a chiral carbon is it's attached to 4 things. Those 4 things have to be 4 different things, which is why this carbon, carbon 6 here at the bottom, even though it's attached to 4 things, 2 hydrogens and a hydroxyl, 2 of the hydrogens are obviously the same thing, so we don't have a chiral carbon there. Now if we look at the center ones, 2, 3, 4, 5, we can see that we do have chiral carbons. So this one's attached to an aldehyde, a hydrogen, a hydroxyl, and this whole thing, right? So that's chiral. So we can indicate that chirality by, usually we put a little asterisk there. This one is attached to the aldehyde plus all of this, and then this on the other side, a hydroxyl and a hydrogen, so it too is chiral. And then this one, same sort of operation, one side, the other side, they're different from each other. And then same with C5 down here. We have a hydroxyl, a hydrogen, this whole thing on one side, this whole thing on another side. It is also chiral. So I have 2 achiral carbons, 1 and 6. I have chiral carbons at 2, 3, 4, and 5. Now because I have 6 carbons, this is a hexose. And because it has an aldehyde at the one end, we would call this an aldohexose. So it's based on the number of carbons, which anything organic based is, and then it's based on kind of what group we have at the top of our Fischer projection there. Is it an aldehyde or is it a ketone? Now the chirality of these things matters because when we have a chiral carbon, what we've learned when we talked about amino acids, for example, as well as other organic molecules that have chirality or chiral centers here, is we can have mirror images enantiomers that are isomers of this thing. So if I had the mirror image of this thing, then I'd have a hydroxyl here and my carbon and hydrogen, hydroxyl, carbon, hydrogen, and I could put them mirror image to each other, right? They're the same reflection of each other, but if I tried to superimpose them on each other, they would be 2 different molecules. So we call them enantiomers. So when we're looking at a Fischer projection, when we talked about enantiomers before, we talked about handedness, meaning are they the left-hand version or the right-hand version? And what we're looking for to determine handedness in Fischer projections is the carbon right before that last achiral carbon. So we're going to identify this last carbon here as achiral. So it's not a chiral carbon. And then I'm going to go second to last to determine handedness. And what I'm looking for is where is the hydroxyl group? And so the what side is the hydroxyl group on in the Fischer projection tells me whether it's D, which is right, or L, which is left. In this case, because I have the hydroxyl group here to the right-hand side of my chain, this would be the D enantiomer. And this is glucose, so this would be D-glucose. If that hydroxyl group was on the other side, then it would be the L-glucose molecule, so L for left. So we're looking for that last achiral carbon. We're going to the carbon before it, and we're looking where is the hydroxyl group. Now, unlike amino acids, which we said are nature likes L amino acids, where it's to the left-hand side, nature likes D carbohydrates. Preferred by nature. So that's kind of a, just one more thing for chemistry students to have to remember, right? L is the magic handedness for amino acids. D is the handedness for our carbohydrates. So the ones that are naturally occurring, the ones that our bodies utilize, these ones are going to be the D of our on our Fischer projections. And I think it's easiest to see the L and the D on Fischer projections, but we can see the alpha and beta on the ring structure, the Haworth structures. So let's talk about how we go from one to the other. So this is kind of the overall view of a Fischer projection. It kind of gives you some information about kind of what's in there, how many carbons are there. These different chiral centers give us information about kind of the different isomers. Now, just as kind of an aside here, every place we have a chiral carbon, we can have a potential for an enantiomer. So this one could be flipped, and that would be a mirror image. This one could be flipped, that would be a mirror image, etc. So as many chiral carbons there are as we can have different mirror images of each other. So that gives us a number of different enantiomers when we get large numbers of chiral centers like this, which means that there's a lot of variability when it comes to sugars, and it matters where these hydroxyl groups are in terms of what larger structures they form, what polysaccharides they form, as well as what their biological functions are in our bodies, and whether or not we can even utilize them in the first place. So that kind of, the idea of enantiomers and stereoisomers and diastereomers, all of these kinds of things are really important when thinking about functions of carbohydrates. Okay, Fischer projections. Now, I'm going to take this guy, and then we're going to wrap it up into a ring. So the convention here for the Fischer projection is that my carbonyl group shoots off to the right. That doesn't really matter, but that's just the way that you're going to always see these things written. So I have that kind of put this way in my structure. So carbonyl off to the right, here's my aldehyde group. When we're going down the structure then, we can kind of see that each of these carbons, because of the four things around them, are tetrahedrally coordinated. So like I said at the beginning, it's sort of like I flattened this thing, and then that gives me this structure. But what that tells me then is that kind of the things that are up and down here, so kind of my up and down along the backbone, are going back into the page, and these guys from side to side are coming out at you, like these guys here. So these guys are coming out at you, these guys are going into the page, these guys are going into the page, this one's coming out at you, these guys are coming out of you, going back into the page, and then we have this achiral carbon down here as well. Okay, so again, the important thing about all of this is that we have models to understand these. We can understand it in 2 dimensions and get information about it. We can look at it in 3 dimensions and get information about it. And now we can go from this kind of projection, this snake-looking 2-dimensional structure, to the ring structure. That's called the Haworth structure, is the ring structure. So Fischer is that projection, the straight line. Haworth is the rings. Okay, so let's talk about the steps in turning one into the other. And I'm going to use the model. And my screen's a little bit limited because this is a big molecule, but we'll do what we can. So if I have my Fischer projection here of my molecule with my little hydroxyl groups that are sticking off, then if I bring my aldehyde group, or the ketone, either one, to the right-hand side, so I'm bringing it to the right-hand side here, and I turn it on its side, then that's kind of step one, okay? So now I have my chain of carbons. I can kind of see how this thing works. I know that when I put it together, it's going to be in a ring. So I'm going to start to coil the end. This is my C6 down here. So the end, this achiral one, I'm going to start to coil it towards the back. So and as I'm coiling this towards the back, then this thing is going to start to form its ring structure. Okay, so that's step two. I brought C6 around. I'm starting to bring this thing kind of towards a ring-like structure. Ring-ish. Okay. Now step three is that I rotate at carbon 5, at least for this one. So it's going to be rotating at the carbon that is the one that we determine handedness from. So we had our C6 is the last one, so I'm going to C5 here. So I'm going to rotate at C5 so that the hydroxyl group is in the line with the ring. So here's my hydroxyl group on C5, and that's going to make this other carbon in the hydroxyl group stick outside of the ring. So this oxygen is going to become part of the ring. This guy's sticking out. So that's kind of step three, if you will. Now we're going to close the ring, but in order to close the ring, I have to take the hydrogen off of this guy. So I'm taking the hydrogen off of the hydroxyl group on carbon 5. I'll just set this off to the side right now. And then I'm going to break the bond of my carbonyl group. Got to put in some energy there. And then I'm going to attach this one here. So now my hydrogen and my oxygen from my double bonded carbon here. I'm going to leave this kind of floppy bond, even though it's not really a floppy bond anymore, but it'll help show which one was double bonded. Here's the carbonyl. And now I'm going to attach this thing to this part. So now here's the oxygen, the hydroxyl from my carbon 5. This is my carbon 1 that did have the carbonyl. I'm going to make it into a ring here. And now I can see that I have a ring structure with 1, 2, 3, 4, 5 and an oxygen in it. Again, that oxygen from carbon 5. And then carbon 6 is sticking off of my ring here. In this case, it's pointing downwards. It could be pointing upwards. It depends on how we join the thing together. Now, if I look at this and kind of where my hydrogen, my hydroxyl group, is located on this first carbon. So this is called the anomeric carbon right here. So that's the one that's attached to the oxygen here and the hydroxyl. So this is a hemiacetal. So if you're kind of familiar with your organic chemistry, hemiacetal formation here with your hydroxyl and the oxygen in the ring. So with this one, because the hydroxyl group is sticking upwards, so here's my ring structure. It's kind of in a chair conformation usually, if I can get it to do that. Oh yeah, there we go. Here's my chair conformation, and it's sticking up. So that sticking up means that it's the beta conformation. If this hydroxyl group, when I put it together, was twisted downwards and on the pointing down side, that would be the alpha glucose. So this is beta glucose, alpha glucose, with the way that this thing is all rearranged and formed together. Okay, so kind of wacky. This guy should probably be on the other side, so there's some issue there. Maybe more like this. This guy's sticking up. Something like this would be the alpha then pointing downwards. So these conformations matter, kind of the sides that these things are sticking off of when these things join together matter. And so we can go from one, that two-dimensional kind of snake-looking projection, into the ring projection, because now when it's in its ring form, we can start to link these things together. And these alpha and beta linkages give us information about what type of polysaccharide we're forming, or what kind of disaccharide we're forming. All right, if you have any questions about this, don't hesitate to reach out. It's an important kind of process. It's important to get your head around the geometries of these things. So take some time to practice, and I'll talk to you again soon.